So then there are three of them are up there, given to us. You can plug in 3, solve for 4.
Yeah. I see where I'm going.
That's okay. Yeah, that's why we're doing it again. So it's M1 V1 equals M2 V2. It was right.
I'm just gonna say.
Thank you. So, dilution problems, the equation is simple, M1 V1 with M2 V2, right? We're given 3 of the 4, plug them in, solve. The only tricky thing was one of our volumes was in milliliters, one was in liters. Doesn't matter which one you use, but they have to be the same. So Ben chose to change 175 milliliters into liters. When I did it on my calculator, I changed 1 liter to milliliters. So I left this as 175 and changed 1 liter to 1,000 milliliters. We got the same exact number. Okay. Who wants to do the next one? Go for it.
The one we don't know, right? The other one's V2, right?
Well, we have,
Because so I thought it was, well, we have M1, but isn't the second one like V2?
well, if you read the question, it says you need to make 10 liters of a 1.2 molar. So this is actually the ending.
That's the ending, yeah.
So that's V2 and M2.
But it doesn't matter to each side.
So the V is volume.
Oh, M, sorry. I'll figure it out eventually. I'm not gonna have time to try. When or not by chance? 4.8. What is it?
Oh, just the half? Oh, not the half.
12.
12.
It didn't sound right, that sounds like, what?
The answer's 4.8.
Would be. Wish I was looking. was falling asleep last class too.
It was at the end, it was at the end. And third one? Sometimes. You have a volume and V1.
Small thing.
No, I think that one should be molar. That one should be V1.
Okay, so. I have it written down, but I didn't do it wrong.
Right.
And can you plug either one of those in to find out the answer? You have two options for 2 milliliters of 10 molar.
Yes, I guess you could. If you did it the other way, well, let's do it the other way. So what she's asking is, the way we did this is we said if we have a 10 molar HCl stock, how much do we need? And the answer is we need 30 milliliters. We only have 13, so no, we can't do it. Okay. The other way to do it is to say, if we are going to use 13 milliliters of our stock, how concentrated would it have to be? So the right side of the equation is going to stay the same. 100 milliliters times 3 molar. On this side, we're going to have M1 times 13 milliliters, and M1 is going to come out to be
I'm gonna do that one.
23, somebody say 6. Once,
3.1.
20, 100 times 3 is 300, 300 divided by 13, there's only one sig fig.
You have 23 point.
Right, but there's one sig fig.
Oh, okay.
So, which means if you're going to use 13 milliliters, you would have to be 20 molar to get the correct concentration at the end. Ours is only 13, so you're not going to get the right concentration. This way of doing it is harder to comprehend what's going on, in my mind.
Yeah, that's what I did.
This way is a lot easier, yeah.
Isn't there an easier way?
You did it differently last time.
Yeah, I got it. Just take this two sides. You know which side's the important one. In this case, 100 milliliters of 3 molar.
Mm-hmm.
Multiply them to themselves. You know, figure out the total. So that'd be
And
300 on the important side.
Mm-hmm.
Other side's 130. Not greater than or equal to, so we can't see.
Right. So that works. What is it, mathematically, what is it that he's doing? Why does that work? So if molarity equals moles divided by volume, What math did you do? What two numbers did you multiply together?
Volume.
Molarity and volume, which equals moles. So what you did is you calculated how many moles you had in your stock and how many moles you needed in your final, and said, I don't have as much in my stock. All three ways work. To me, this way is the simplest, and it involves the least amount of thinking. If you have a good grasp of the concept, Ben's way is a good way to do it. But you have to have a good grasp of the concept to know what's going on. Okay. So let's move on. I think we did the dilution factors. The last thing we have to talk about are called colligative properties. These are another one of those things that you use occasionally, you just don't know it. Okay? A colligative property is something that does not depend on what type of a solution you have. All that matters is the concentration of the solution. It matters the concentration of the solution, and more specifically, how many particles are in that solution. So, if you dissolve 1 sodium chloride in NaCl, how many particles do you get out of that? 2. There are 2. If you take an NaCl and you dissolve it in water, it breaks up into ions, right? How many particles, how many pieces do you get? 2. You get a sodium and a chlorine. If you dissolve calcium chloride, how many pieces do you get? 3. A calcium and 2 chlorines. Calcium chloride is CaCl2. Okay? That's what we mean by particles. If you dissolve sucrose, how many particles do you get? 1. Sucrose is molecular. It doesn't break apart. Only ionic compounds break apart. Okay? So what's going to matter here is not that it's sucrose, not that it's sodium chloride, not that it's calcium chloride, but just how many particles you get out of it. So a sucrose solution that's twice as concentrated as a sodium chloride solution is going to have the same number of particles. They're going to behave the same. There are 4 of these colligative properties. First is osmotic pressure. There's vapor pressure lowering, boiling point elevation, and freezing point depression. We'll talk about each one. Like we said, what these properties are related to is how many particles are in the solution. If we're dealing with the strong electrolytes, like sodium chloride, calcium chloride, the particles are the number of particles are just how many ions are in there. Magnesium chloride, you get 1 magnesium, 2 chlorides. Magnesium chloride, you get 3 particles, right? So, in this question, we have a 1 molal solution of magnesium chloride. What is the concentration of ions? Doesn't matter what type of ions, ions as a whole. What is the concentration of ions in a 1 molal magnesium chloride solution? You don't even have to know what the molality equation is. You don't need it. 3. You have 1 molal magnesium chloride times 3. There are 3 particles. There's 3 molal solution of particles, or ions. Just take the concentration, multiply it by how many particles you get from it, and that is your concentration of particles. First one we're going to talk about is actually, it's in my mind, it's the hardest to comprehend. Okay? Also, according to the learning objectives of this course, it's the most important one. Okay? You've heard of osmosis. You've possibly heard of reverse osmosis. Maybe you've heard of reverse osmosis, but not actual osmosis. If you were to look, you took the label off your water bottle.
It was Pepsi.
Oh, it was Pepsi. Okay. If you look at a water bottle, it may say purified by reverse osmosis. Can you find it on there in small print?
It's on here somewhere.
It's probably on there somewhere.
Oh, some paper distilled.
Oh, fancy.
Fancy.
Okay. So osmosis is the ability of something to diffuse or move across a membrane that will allow some things through but not other things. In general, only really, really small things can get through, bigger things can't. It's like a microscopic screen. Okay? If you put a screen on your window, pollen unfortunately can get in, but mosquitoes luckily cannot. Right? So a membrane is like a microscopic screen. There are little tiny spaces that small things can get through. Normally what we're going to be dealing with are water solutions. Water can get through this membrane. Anything dissolved in the membrane cannot. Okay? So we call this a semi-permeable membrane because some things can get through, some things can't. Here's our membrane. Solvent molecules are water, they're small. There's something big dissolved in the water, it's not going to fit. Water is the only thing that's going to go through here. What happens is water wants to go one way or the other. What we're going to see is water wants to go where the solute is. So in this situation, the water is going to want to come over to this side where the solute is. Okay. If you were to make up a little apparatus, you have a semi-permeable membrane on the bottom, and you have a salt solution inside. You put that in pure water, the water from the beaker is going to go inside your apparatus and make the level rise. Okay, it's going from here, now it's up to here, because water from the beaker went into here. But if you were to push down on this water here, you could force that water back out into the beaker. And that amount of pressure you would have to push with is called the osmotic pressure. Here's another way of looking at it. If we have a U-shaped tube, with a membrane right in the middle, and then we pour two liquids on either side. On one side we have just water. On the other side we have, say, a sodium chloride solution. Eventually the water on this side is going to move over to this side. So now this side is higher. If we push here, we can push it back through over to here. There are two ways to measure that pressure. You can either measure it by how much you would have to push to equal it back out, or you can measure the distance between. Okay? You don't have to worry about any of this, but you have to worry about understanding what osmotic pressure is. It's a matter of the water molecules wanting to go where the solute is. Okay? We can calculate this with this equation. Okay? Have an idea of how to do this, but don't stress over it. Okay? If that gives you any sort of hint for anything, don't stress over this. To calculate osmotic pressure, we have pi equals IM/RT. Pi is osmotic pressure. I is just the number of particles that you make when you dissolve whatever your solute is. For sucrose, it's 1. For sodium chloride, it's 2. Calcium chloride, it's 3. R is just our same gas constant, 0.0821. And T is just temperature in Kelvin. Plug and go, okay? There is a term that some people use called osmolarity. And osmolarity is just like molarity. Molarity is moles per liter. Osmolarity is osmoles per liter. And an osmole is I times M. It's just that concentration of particles that we were talking about. That is an osmole. Here's an example how to calculate this. We have to make 1.5 liters of a glucose solution because we're going to give it to a patient through an IV. Osmolarity is very important when you put something in the body. Otherwise, we'll see it on another next slide probably. We have to match the osmotic pressure of the blood. If we make our glucose solution with an osmotic pressure different than the osmotic pressure of blood, bad things are going to happen. Okay? So, this tells us the osmotic pressure of blood is 7.65 atmospheres at physiological temperature, 37 degrees. Which means our osmotic pressure of our glucose solution has to be 7.65. There is no other way around it. Has to be 7.65 equals IMRT. All we have to do is find which of these variables we're solving for. The other ones have to be given to us, plug them in. Which one of these are we trying to solve for? M. Okay? So the question is, how much glucose should you dissolve and how much water? That implies grams. This is the concentration. What we have to do is we have to solve for the concentration, then we can figure out the grams. So what is, in this situation, with glucose, what is my value of I?
1, 4. 1.
So,
12 and 6 again.
glucose is like sucrose, it's molecular.
Oh, yeah,
It's one.
it's 1.
I'm impressed that you remembered the formula for glucose.
I just got out of biology.
So, in this case, I is 1. So mathematically it disappears. M is what we're looking for. What is R? It's our gas constant. 0.0821. T has to be in Kelvin. We're at 37 degrees Celsius. So we're at 37 Celsius. 10.15 Kelvin. So we solve for M, and M comes out to be what? Everybody get 0.3? I figured people had done it, they just weren't confident enough to say it. Well, once I say a number, then you're
What did
confident
you
to
say?
0.3,
No, what is that? I got
7.65.
3.3.
I got 3.3.
I got 0.3004.
So
That's
7.65 divided by 0.0821 divided by 310.15, so 0.3043.
Oh, I should have did, I
Whoops.
divided that
I
number
multiplied
by
the side
7.
and divided by 7.
Yeah. Did it
So
backwards.
M
So wait.
equals How many sig figs?
1.
2. 0.37 molar. So we solve for a concentration. The question is, how much glucose should you dissolve and how much water? What is the formula for molarity? Because that's what we have here is molarity. Liters, yes.
But how would you?
Teamwork.
How would you know to divide them in liters? I guess that's where I'm confused.
It's just algebraic.
It
You
is,
can multiply the R and T and then divide that number.
Yeah, you could do it that way. Just in
Divide it wrong.
a non-scientific calculator, it's easier to do it one at a time. 0.30 molar equals moles of glucose over liters of solution. All right? Do we have either of these? Which one? Liters. So, we have liters. So now we have 0.3 equals moles of glucose over 1.5 liters. Moles equals 0.75. No, 1 point, no, 0.45. 0.45.
0.45.
0.45 moles of glucose. Okay. We're going to leave it in moles. We're just going to say you need to dissolve 0.45 moles of glucose in how much water? 0.3 times 1.5. How much water do you have to dissolve that 0.45 moles in? This is one of the technicality, make it and do it right in the lab type things. You dissolve it in enough water to make 1.5 liters of water. 0.45 moles of glucose is quite a bit. That in itself is going to have a substantial volume. So if you add 1.5 liters of water, your total volume is not going to be 1.5. So on an exam or something, the correct answer is sufficient water to make 1.5 liters of solution, or something along those lines. We said that osmotic pressure is really important in the body. The easiest way to see this is with red blood cells. A red blood cell normally has this kind of dimpled donut shape. Okay? It's round, in the center there's a divot. Okay? If you put it in a solution that has the same osmotic pressure as the osmotic pressure in the cell, nothing changes. We call that an isotonic solution. Iso means the same. Isotonic solution has the same concentration inside as outside. In that situation, the blood cell wouldn't change. If we put it in something called a hypotonic solution, in this case, the concentration inside the cell is higher than the concentration outside the cell. And we said that the water wants to go where the solute is. In this situation, where is the solute? Inside or outside? Inside. The concentration is higher inside than outside. The solute is inside, which means the water goes in. And you get a blowed up blown up blood you get a blown up blood cell. It blows up like a balloon. Okay? The opposite of a hypotonic solution is a hypertonic solution. Hyper means high, hypo means low. A hypertonic solution, there's more solute outside than inside. In that case, where does the water want to go?
Outside.
Out. The water that's inside goes out. So what you end up with is a shriveled up red blood cell. So this is why you wanted to match the osmotic pressure in the patient's blood. If you don't, the blood cells are either going to turn to that or that. In either case, you're getting sick. Right? Next colligative property is vapor pressure lowering. What is vapor pressure? We talked about this.
It's gone now.
The diagram is stuck above the picture.
You're on the right track.
There, I just can't put it into words. Words are hard.
Has to do with what?
Operation?
Yes.
Hey, there we go.
I don't know what though.
So,
Zero.
if we,
Stop before it's done.
if we have a beaker filled with water and we put it in a sealed box, okay?
Yep.
The vapor pressure is the pressure that the water wants to make up in the gas here. It will evaporate until this gas reaches the vapor pressure of water. Okay. So if you raise the vapor pressure, what that means is at whatever temperature you're dealing with, more of your liquid is going to go in the gas. If you lower the vapor pressure, that just means less of it is going to go in the gas. It's going to stay as a liquid. Okay? So the colligative property is vapor pressure lowering. So when we add something to this solution, when we dissolve something in here, it prevents the gas molecules from escaping. That's the gist of it. There are two types of solutes that we can have. We can have a solute that is volatile or ones that are non-volatile. A volatile solute is something that will form a gas. If we have a solute that forms a gas, it's just going to leave itself. And then we're back to where we started. So in this situation, this only applies to non-volatile solutes, like sodium chloride or glucose or sucrose, things like that. Pretty much everything we would normally deal with is a non-volatile solute. When we add a non-volatile solute, it lowers that vapor pressure. Okay? If we have this beaker, to say this is just water. In here we have liquid water. Here we have water vapor, or gaseous water. If we dissolve something, I have no idea what that is, but it's something yellow. We dissolve in that water. We now have less of the water molecules up here in the gas. You see that? That's what vapor pressure lowering does. It makes the solvent, the liquid, stay a liquid. Another way to look at this, if we have our same container, we have a beaker of water and a beaker of sugar water. Put them in the same container. Which one is going to have a higher vapor pressure? Pure water or sugar water? Pure water, because the sugar lowered the vapor pressure in the sugar water. Okay? Which means more of the pure water is going to come up here. And what's going to happen is it's actually going to come up here and then end up in the sugar beaker. So over time, the water will actually transfer from this beaker to that beaker. So if you ever want to do a really long magic trick, you can bet someone that you can make the water go from that beaker to that beaker without touching either of them. Next thing is boiling point elevation. This is very, very, very similar to vapor pressure lowering, and you can make a case that's actually the same thing. This means when you dissolve something in a liquid, when you dissolve something in water, the boiling point of that liquid goes up. Okay? When we add a solute, it makes the boiling point go up because the vapor pressure went down. The boiling point is the temperature at which the vapor pressure equals atmospheric pressure. If you try to rationalize this all in your head, you'll realize when you lower the vapor pressure, you're going to have to heat it more to get that vapor pressure up to atmospheric pressure. If you have to heat it more, that means the boiling point is now higher. Okay? In the end, it's the same thing. When you dissolve something in it, it wants to make that liquid stay a liquid. Okay? If you remember that, you'll be safe.
Does this also tie into the osmotic property because it wants to be with the solute?
Yes. That one is that relationship is harder to see, but you are correct.
They all come back to it wants to stay with the solute.
Which is why they're all colligative properties under that same umbrella. Yes. Here's the equation. Don't worry too much about it. Okay? I just want to show you how simple these calculations actually are, and if you were to do it, what it looks like. Delta T. What is delta? What does delta mean? Change. What do you think T is? Temperature. B, sub B means boiling point. TB is boiling temperature. Change in boiling temperature equals KB times M. What is lowercase m? Molality. K is a constant. Every different solvent, water, ethanol, whatever, has a different K value. Take that constant, multiply it by your molality, boom, you have your change in boiling point. These are actually very simple calculations. We use this to boil spaghetti. You ever put salt in your pasta water? Yes. You would actually probably have to put a lot of salt in there to actually taste salt in your pasta. The biggest reason you add salt to the water is to make it boil at a different temperature. If you add salt to that water, is it going to make it boil at a higher or lower temperature? Higher. Which means your pasta is going to cook faster.
Yeah. Yeah, the picture cut out our slides. So I just wanted to cut this
Wait, your slides have the picture?
Yeah.
again.
Yes.
We're on the notes now.
I really don't know. I really don't know.
Okay.
Yeah, so I can see on his next slide, the whole next one, I deleted these stupid pictures.
Maybe not the original one. After you updated
Yeah,
it.
we
maybe.
still, I printed those two plates.
Yeah, yeah. No, I know. I know.
Yeah, Phil's the word.
So the fourth one is freezing point depression. Again, when you dissolve something in a liquid, it makes it want to stay a liquid. Okay? On the other two, we will keep preventing it from going from liquid to gas. In this one, we're preventing it from going from liquid to solid. It's the same exact equation. It's just you have a different K value. The K constant times the molality is your change in freezing point. How many people have lived up north? Quite a few. Did you know why they put salt on the road? To melt the ice, but scientifically, we're in chemistry class. We want a better answer than to melt the ice. Why does it melt the ice?
It lowers the freezing temperature.
It lowers the freezing temperature of the water, which is why on the really cold nights, they don't bother putting salt down. Because you're still going to get below the freezing point of salt water. So why waste the salt? In those situations, you put down sand, just provide traction on the ice. Okay? You can also add salt to ice. What's the purpose of doing that? It makes it colder.
So how do you do that?
Yeah, exactly. Exactly. So if you have just ice water in here, it's going to be 0 Celsius. Okay? If you add salt, the freezing point of water goes down. Let's say you add enough salt to decrease the freezing point 10 degrees Celsius. Your ice water bath is now going to be negative 10 degrees Celsius, which is going to make your drinks colder and get them cold faster.
And you don't have to salt your margarita glass. It's pretty salty.
I'm not sure why you'd have a margarita glass in a cooler of salt water.
Hard times.
It's so neat.
Yeah, I can't wait to get mine.
Got like a radio,
Blender.
blender. Look at the coolest cooler.
So here's just a very quick example. If you want to calculate the freezing point of a 1.5 molal solution of sucrose in water, it's just 1.5 molal times the constant which would have to be given to you. You just no way of knowing that other than it being given to you. 1.5 times negative 1.86, which is our constant, equals negative 2.79. So our change in our freezing point is negative 2.79 degrees Celsius. So what is the freezing point of this water? Negative 2.79, because it was started at 0. 0 minus 2.79 is negative 2.79. That's how those calculations work. Don't worry about them too much. Okay?
And then it's not going to be on a quiz like this?
I'm not saying that, but don't stress about it. So, I'm not going to verbally say that it is not on a quiz or an exam. Wink.
So you're mostly saying that because one of the answers are going to be, or one of the, it's going to be in the question. Like they got to give you the 1.86 Celsius.
Yes.
Correct.
Yes. These equations won't be on the cheat sheet, but you also don't have to memorize them.
Okay. Awesome.
Here are 3 solutions. 0.2 molar sodium chloride, 0.5 molar sucrose, and 0.3 molar sucrose. Which one of these is going to have the highest boiling point? This is one of those thinking ones.
A?
Why A? They dissolve. They dissolve, they don't dissociate, they don't break apart.
I'm guessing there's less there, so
It's B.
Why B?
Because even if you have 2 particles per NaCl, it's still 0.4 molar, and it's still greater than 0.5 molar.
Exactly. Boiling point, the one with the highest boiling point is going to be the one that has the most boiling point elevation, which is determined by how many particles there are. So the concentration of the particles in here is 0.5, because each sucrose is only one particle. The concentration of particles in here is 0.2 times 2, because you get a sodium and a chlorine, is 0.4, and that one is 0.3. That one's the largest one. That has the most particles, you get the largest change in boiling point, and that gives you the highest boiling point. Which one will have the lowest freezing point? B. Freezing point is another colligative property. Freezing point depression. The more particles you have, the lower your freezing point is going to be. B has the most particles. So just it all comes back down to the more particles you have, the more it wants to be in the liquid state. You're going to raise the boiling point, you're going to have to heat it more to get it to boil. You're going to decrease the amount of molecules that just randomly come off to form vapor. You're going to lower the temperature you have to cool it down to make it freeze. It wants to stay at the happy medium liquid in the middle.
Just realized the slide says A for both of them.
Yeah.
Yeah.
It's B.
I do just like yellow and trying to see how
So it all comes down to the particles.
Yep, it's the number of particles. Which one of these would have the lowest freezing point? Calcium nitrate. That one you get 3 particles. That one you get 1 particle. That one you get 2. They're all starting at the same concentration. So the one that gives you the most particles is going to give you the highest particle concentration. That is the end of that.